Hello everybody, welcome at IPCMS. My name is Stefan Haacke. I'm 57 years old, a professor in physics at Telekom Physik Strasbourg. I'm here at IPCMS since 2004. IPCMS was created 35 years ago as really the first interdisciplinary institute in material science gathering physicists and chemists. Today there are 230 people working at IPCMS, 120 of them are permanent. The institute is organized in 5 different departments, but also in 5 different topical axes. Ultrafast science is performed in all 3 physics departments, but more specifically at the DON, the Department of Ultrafast Optics and Nanophotonics. Our team, BIODYN, is composed of 2 permanent researchers, Jeremy, Léonard and myself. Currently we have 3 postdocs, 2 PhD students, and in the summer period now 4 interns. Our research can be divided in 3 different axes. Biophysics on one side, photo-isomerisation like in retinal proteins, and organic materials for renewable energy production using sunlight. Most of our techniques is ultrafast spectroscopy in the near UV visible near infrared range. And for that we investigate transient absorption changes, but also ultrafast fluorescence.
My name is Jeremy Léonard. I am a Léonard S research director, and I am the head of the small team that we make together with Stefan Haacke. I will introduce you to a setup that we have been developing to do transient absorption on molecules. This is a setup designed to achieve sub-10 femtosecond time resolution. The signatures of the vibrational motions of the molecule show up as oscillations in the absorption spectra, so we can follow the vibrational motions along the photoreaction from the excited state to the photoproduct formation. We start with a titanium sapphire amplified laser system from Amplitude. It operates at 1 kHz repetition rate. It produces 3 millijoule pulses, and we use 1 millijoule to inject a hollow core fiber which is filled with argon gas. The nonlinear propagation of the 40 femtosecond pulse inside the gas is going to broaden the spectrum of the pulse, and with chirp mirrors we can recompress this pulse down to 6 to 8 femtoseconds, depending on the gas pressure. Next to this red to near-infrared very short pulse, we use the fundamental pulse that we propagate through an interferometric filter to narrow its spectrum down to about 1 nanometer, so it makes a 1 picosecond long pulse. And we generate a blue pulse by engineering the sum frequency between the short pulse and this second long pulse. The interest of doing so is that we can tune the spectral phase of the broadband blue pulse by tuning that of the short red pulse. We overlap both the short and the long pulse on this polarizing beam splitter. They have orthogonal polarization. We co-propagate both pulses through a piezo delay line, which allows us to tune in what we call a fast scan, the pump probe delay. This pulse is used in our experiment as a pump pulse, so it travels through this chopper, which is here to extinguish every second pulse. These 2 pulses then are focused inside a BBO crystal, where we implement type 2 sum frequency generation to generate a very broad blue pulse, which can then be as short as about 8 femtoseconds. As a probe pulse, we generate a white light supercontinuum in calcium fluoride. So we have the full spectrum from 300 nanometers up to about 800 nanometers. We use this pulse as a probe to follow the transient absorption of the molecules which are excited by the blue pump. In order to further reduce the noise in our experiment, we also implement a reference beam. So this white light is split into 2. So in the end, we have a detector which is composed of 1 prism spectrometer to disperse light of both pulses, the probe and the reference, which are recorded on 2 independent CCD cameras. The sample in most of our experiments is this kind of flow cell where we circulate with a peristaltic pump the molecules in solution. Presently, we are upgrading this experimental setup to a two-dimensional broadband spectroscopy setup. So we use the same probe pulse, but now the pump is a pulse pair. We use this so-called twins device, which is an interferometer, where we can control the time delay with interferometric accuracy.
Hello, my name is Emira Garbi. I am a PhD student of Jérémy Léonard. I work using the upconversion setup and the STREC camera setup. The upconversion spectroscopy is a precious tool and is complementary to transient absorption spectroscopy. The interpretation of upconversion spectra is more straightforward because the obtained signal comes from the signature of only the excited molecular states. Here we perform upconversion fluorescence spectroscopy with a time resolution of 200 femtoseconds. The fundamental 800 nanometer is used in order to pump a commercial OPA that can be tuned from 200 nanometer to up to the near infrared. For the upconversion fluorescence setup, we need two beams, the pump beam and the gate beam. The pump will excite the molecules in solutions that are being circulated in order to avoid photobleaching. The fluorescence coming from the sample is collimated and focused onto a BBO crystal using a pair of parabolic mirrors. The gate beam of 60 femtosecond time duration is also focused into the BBO crystal and used in order to sample the fluorescence at different time delays. The upconverted signal that is obtained from some frequency generation is guided towards a fiber and towards the detector, and the spectrally resolved signal is recorded using a nitrogen-cooled CCD camera. Our STREC camera-based experimental setup is situated in a different room. So we use a Tangerine commercial laser to pump a home-built OPA that can be tuned from 300 nanometer up to 1030 nanometer. After the OPA, the excitation beam is polarized for the purpose of the population decay measurements. The collimated beam is reflected by the dichroic mirror, goes through a microscope objective that focuses it onto the sample. The fluorescence is then collected by the same objective, transmitted by the dichroic mirror, and is guided either towards a CCD camera in order to image the beam spot, or guided and focused onto the entrance slit of the detection stage. Another polarizer is used on the detection path in order to have a relative angle between the excitation and detection set to magic angle. The detection stage comprises a spectrograph in conjunction with a STREC camera of a 10 picosecond time resolution that allows us to measure spectrally as well as temporally resolved spectra. We use two different time resolution fluorescence spectroscopy techniques in order to fully characterize the mechanisms of energy transfer inside the nanoparticle, which are the anisotropy decay that occurs on a femtosecond time scale measured using the upconversion spectroscopy setup, and the population decay that we monitor using the STREC camera in order to retrieve the exciton diffusion time scale within the nanoparticle that would be on a picosecond time scale.
You've seen the diversity of the different laser sources and setups that allows us to address processes from sub 10 femtoseconds to 10 milliseconds. There's a large variety of really fundamental problems like the coupling of electronic and nuclear motion for the so-called non-adiabatic photoreactions, but also slower processes like charge transfer, energy transfer for all kinds of functional materials are important. The current developments in our team concern two main avenues. One is the so-called two-dimensional electronic spectroscopy. It will allow us to address better the coupling between nuclear motion and electronic or excited state dynamics. Second avenue is a femtosecond photoelectron spectroscopy in liquid jets, not in gas phase but in liquid jets. So that's a development that we have with Oleg Kornilov at the Max Born Institute in Berlin. So there's a promise that this will in particular allow us to investigate the conical sections, the energy landscape around it, and how the energy landscape can be modified through chemical design of photo switches or through solvent properties.